using of Josephson junction as comparators because of due to nonlinear characteristics of Josephson dynamics, digital applications in and using of Josephson junction as qubits in quantum computing. Quantum computing here, very nice review of Likarev. And here, what it is sampler? Sampler is this one measurement of form of very weak signals. Here we have a comparator. This one may be single Josephson junction and maybe balanced comparator. And here we have three signals: feedback signals, measured signals, and signals of this one measured signal EX and strobe pulses. Strobe pulses, and here such systems, and our aim is estimating time resolution using basic equations of Josephson dynamics. And here I would like to mention about first version of Josephson sampler system, and as you can see here we have two junctions Josephson interferometer, and here we have comparator based on single Josephson junction, but this Josephson junction is different. Critical current of this Josephson junction is lower than this one. This one in this schema they serve for the obtain of strobe pulses. Strobe pulses is good strobe pulses, and balanced principle of investigation of using in semiconductor systems was introduced many years ago, and using of Josephson junction as nonlinear element in superconducting electronics also firstly in Soviet time was introduced by Bastir and in the Moscow State University laboratory. And here I would like to mention that last years there are any quantum limitations of balanced comparators because of, as you can see, in the case of balanced comparators, if we take two identical Josephson junctions with identical characteristics, fluctuations in this schema, in this picture, does not affect on time resolution and another characteristic because of if we use measured signals to this point, in this case, due to that fluctuations in this schema is the same, and exclusion of thermal fluctuations in this case arises, and as a result, such systems can acting as quantum object because of here only quantum fluctuations can influence on the result. And from this point, and here there are also slides of Likarev, Ortlev, also which came to our conference, and Ali Ozbey from Turkey, and here another study related with properties of balanced comparators, and here I would like to say that, as I said before, in this balanced comparator at low temperatures, we have very low gray code, gray zone. It means that there are a small area in which two elements of Josephson junctions, two junctions, switch into resistive state simultaneously. And here, for the expression of time resolution of balanced comparator, we should calculate transfer characteristic of size junction. It means that we use in input Heaviside function, and using fundamental equations for dynamic Josephson phase can calculate some characteristics. Here I present transfer characteristics of Josephson junctions. It means that in the case of Josephson junction we have three components of current. This one displacement current, this one Josephson current, and another current of quarter particles, and due to that here we have full component of resistivity, capacitor, and inductance. Here we have oscillation character of the transition, characteristic of tunnel Josephson junction, and time resolution is determined as time between level 0.1 and 0.9. This one definition of time resolution, and using this methodology we can calculate if you can calculate transfer characteristics of from comparators, we can estimate time resolution. And here I would like to mention that last year's people using overdamped Josephson junctions. It means that in the case of overdamped junctions, we can neglect it by the first term. And last year's there are anharmonic effects on current phase relation. It means that up to now in the study of Josephson technology, Josephson dynamics, we use this one simple Josephson dynamics. This one related with capacitor of, which is proportional to capacitor of Josephson junction, second derivative, first derivative, and in the case of small capacitor, delta tends to 0 and can neglect this one, and in this case inertial properties of junction becomes more good, and it means that for the modeling of such system in general case, for tunnel and for overdamped Josephson junctions, we can use in general case such system of equations. It means that here we have EX measured signal, and here as you can see this one current which related with stroke pulses. Stroke pulses that we take linear drawing of current, external current, which applied from the generator of stroke pulses. But here we have measured signal, and this one we're using such simple systems, and we can after some manipulation in the case of small current, measured current and stroke pulses, we can obtain for system of two differential equations. It means that here we have for the difference of phase, Josephson phase phi1 and phi2. Delta phi, it means phi1 minus phi2. It means that in this case we have four difference of magnetic phases, Josephson phase size equation, which related with measured signal, and here if we take a Heaviside function, then we can calculate transfer characteristic of the comparator. In our case, second equation related with the changing of dynamics using stroke pulses. For the calculation of phase dynamics in the case of tunnel Josephson junctions, it means beta is higher than 1. In this case, we use Singirev results. Many years ago, he take classical results with sine sphere tunnel harmonic case. and here we have wrong sampling rate is very slow. It's very slow. In this case, matching of solution of this differential equation in different points, he gets such results, and from this, using this result, we have taken some results at least with time resolution of which, as you can see, is proportional beta. Beta, it means that Mach-Camber parameter related with capacity of Josephson junction. Josephson junction, and here, in the case of Josephson junction with non-linear anharmonic current relation, it means that here we should take into account seconds, alpha sinus 2 phi, because of last year, as I say, in D-wave superconductors and two-band superconductors, there are effects related with in Josephson junction. We have seconds amplitude, and such second amplitude leads to increasing of effective critical current of Josephson junction. What it means, effective critical current? It means that in this case, critical current is determined as maximum of supercurrent, because of we take sinus phi and alpha sinus 2 phi, and as you can see here, inclusion of second anharmonic parameter leads to increasing of such effective critical current. It means that due to that critical current is renormalized, time resolution of Josephson balance comparator also should be rewritten. And using these results, we can calculate. Just a moment. No, yes. As you can see, time resolution of tunnel Josephson junction for different sampling rate, as you can see here, 1, 2, 5, and 10. Here, as you can see, time resolution became better because of time resolution here is determined by the sampling rate. This one related with stroke pulses. This one in the case of tunnel Josephson junction, in the case of Josephson junction with high Mach-Camber parameter. But in the case of single flux quantum, we have used standard single flux schemes. It means that in this case, area of single flux quantum is equal flux quantum, and in this case we have only one picture because of in the case of we take that single flux quantum has triangle form. This one first left side is linearly growing stroke pulse. And in this case, here we have only one this one coefficient 0.64, and here as you can see 50 over critical current for effective critical current for such Josephson junction with anharmonic anharmonic current preservation. This study and the result calculation in the case of overdamped Josephson junction, it means that in this case beta is very small and we can neglect it by the first term and can calculate time resolution in this case. And the results show that using Josephson junction with anharmonic current preservation leads to improvement of time resolution, which relates with anharmonized parameters, increasing of critical current of, in this case, for the case of anharmonic currently in relation to those junctions leads to lowering of Josephson inductance. It means that when inductance phi 0 over critical current, when critical current is increased, then inductance, Josephson inductance is decreased. And slight decrease leads to improvement of the time resolution, which can be at the level of time. Because of, as I say, this Josephson junction, this balance comparator can be used in quantum computing and rarely in normal classical, but Josephson junction based normal classical computation. Thank you. This one different than theoretical computing, but related with that, like yes, please.
I have a technical question. Mathematically, it looks very nice, but I assume that you put all this equipment to, for example, liquid helium, and the question is, will it work these chips and transistors in that very low cold temperature?
But here I show one, just one minute. This one. This one, this study, and in this study people use this one, Josephson junction with unharmonic current acceleration as qubits realization, and here he found that, as you can see at this millikelvin area, the ratio of second harmonic to first harmonic here increasing because of this one many low temperatures, and due to that quantum bits and quantum effects became important in this area. Using this result, I calculate and show how time resolution will be changed because of sometimes experimentators they ask especially this question, how many times? 10 times, 200 times, 1,000 times. And here I use numerical equations and we calculate time resolution.